We're going to talk about segment and angle bisectors. Do you know what the word bisector means? What do you think? Yes, sir. Well, kind of, yeah. It's kind of like that. What does it mean to dissect something in biology?
Cut it open.
Okay, cut it into pieces, right? Okay, typically, you can take it apart, cut it into pieces, and explore the pieces, right? Okay, so to bisect something is similar to that in geometry. When you bisect something, you are cutting it into how many pieces? Two. And what do you suppose is going to be true about those two pieces? Okay, now we have to be careful with this. The pieces are going to be congruent, right? Because the pieces are geometric things, right? Like if we bisect, let's say, a segment, for example. We're cutting it into two smaller segments, right? And segments are things, and so we'd say segments are congruent, right? So we're going to cut it into two congruent pieces so that the measures of the two pieces are equal. Good, because measures are numbers, and numbers are equal. You understand what I was getting at there? Congruence is a property in geometry of geometric things. Equality is, like in any part of math, is a relationship between numbers, between values, okay? All right, so moving on here, let's take a look at this. So our objectives here, we want to get to the point where we can bisect a segment and bisect an angle. And this is, I think I'm going to try to have you guys do a little geometry lab on this using Geometry Sketchpad. I'm going to try to set that up and see if it's, I got to work through all the, it's kind of a weird thing to do in a high school geometry class, so I got to figure out how it's all going to work. But I'd really like to try it with this section. I'd like to have you do some constructions using that software, which you're really going to like. It's Geometry Sketchpad, and I'll take you through a little tutorial maybe later this week and just kind of show you how it works. But it's good for a couple of reasons. It's good because it kind of at a real basic level, kind of at the most obvious level, it illustrates the points that we're talking about in class. So it's good. I mean, it fits in with the geometry that we're exploring. But beyond that, it does some other things that I think are interesting and important. It is kind of like programming a little bit. When you use a program like this to do constructions and to build things, you have to follow a very strict protocol. I mean, you have to know how to create things based on smaller tools, and that is like an object-oriented programming session in a way, which is something we don't get enough of in our district, I believe. And I'd like to expose you to any opportunity I can where you get a little bit of a hint of what it's like to think like a programmer. That's a hugely important skill for you guys in your futures. And so it does that. The other thing it kind of does that I think is interesting, especially if you have any interest in graphic design or in architecture or engineering, is it gives you a chance to use a program that is similar to like a CAD program, where you're actually having to go in and mathematically create very precise things in an organized way so you come up with a product. And so I think those sort of peripheral skills are things that you'll enjoy. I know you guys all enjoy doing it. It's fun to work with, but it also, I think there's some important reasons aside from just strictly the math why it might be useful for us to use that program. So just a little heads up. All right, so how do we do this stuff? So you always remember, if they are congruent, then their measures are equal to each other, right? We already kind of touched on that. So midpoint, first of all. It's the point that bisects a segment. So that's really annoying, isn't it? I just borrowed this one. I didn't make this one. So it splits it into two equal pieces. So for example, what if we've got a situation like this where I've got segment AB and we're told that M is the midpoint, right? So M is the point that bisects the segment, meaning it splits it up into two congruent segments, two segments that have equal measures. What is this all about? Oops. Oh, it's way off. What's going on? Hang on a second. Okay, what is this stuff all about right here? What do those symbols mean? Anybody know? What do you think, Duncan?
It's the line that bisects between the points M and then M and B.
Okay, so you mean, say that again. I think you're gonna say the right thing, but just say it more clearly. So what about AM and MB then?
It's the line that's in between those two. Is it quarters?
Okay, not exactly. Maybe I'm trying to figure out what, these are just symbols. So all these things are, these little hashes here. What do you think? Yeah, they're congruent symbols. That's exactly right. So let me make them a different color so they maybe stick out a little bit. But these are just saying that the two smallest segments that they're sitting in, so for example, this represents segment AM, right? And this one represents segment MB. It's saying that those are congruent, which just means in this case that their measures are the same, right? Make sense? Okay. Those are congruent symbols.
What if there's like more than one line for like congruent, like not like 3 lines that are like what if there's like one pair of congruent lines and then there's another?
Okay, so I see what you're saying. So no, good point. So what if we had, I'll be drawing on here. So what Jill is saying is, what if we had some other lines? Like let's say we had.
But they were on the same like.
Okay, so what if we did this? Like we had CB, how about? And let's say we had also, that's D. Say we had DB, and we know that those two are congruent also. That's what you're asking. How would we show that those two are congruent to each other, but not to those two, right? Very good question. So what do you think? How might we do that? Yeah.
Okay, that's what I was thinking.
Like that, yeah, good. So the two go with the two and the one goes with the one. Okay, good question. All right, so now, given this information, let's say we attach some algebraic expressions to the lengths of those segments. So this is it's kind of not a super difficult example, but it's a good example of the kinds of things I'm going to want you to do again and again in this geometry class. I want you to be able to harness your understanding of geometry to set up a geometric relationship that we can turn into an algebra equation and solve for x in this case. Okay, so we want to find, I guess what we're trying to find here is solve for x, but what if those instructions weren't even there? What if what we really wanted here was just to find the length of AB? Just pretend. I kind of in a way, I wish I wouldn't have had that on there because it'd be better without. But let's just do this. Pretend those are gone. How are we going to find, does that seem like a problem? Because we're not given the value of x, are we? Right? At first glance, does that seem impossible to do? Well, you guys are really smart, so it probably doesn't seem impossible. But you see where before your mind attaches to this problem and really starts to be analytical, that seems a little bit of an issue because we've got x's here and we don't know what x is, right? If we want to find the length of AB, what's our strategy going to be then?
Put 12x plus 3 equals 10.
Okay, good. We've got to set up an equation here based on the geometry relationship that allows us to solve for x. We know that these two segments are congruent, so their measures are equal, and so we can set them equal to each other. Right? Set them equal. What are the steps in order we do to get the x by itself? Okay, good. Subtract. Get the x's on one side, subtract 10x, subtract 3. So what's x equal to? 1. So if x is 1, then what's going to be the length of AB? How are we going to know?
3 plus 15.
Daphne, go ahead.
You substitute x in, so it's just 12 plus 3 plus 10 plus 5.
Okay, good. So we substitute how we might say this in math. We're going to evaluate this expression when x equals 1, right? And that's going to give us 12 times 1 plus 3 is 15. And do we really even have to evaluate this one then? We don't, because we know these are the same, right? And so 15 times 2 is 30, and we got it. Okay, make sense? Okay, yes, sir.
couldn't you evaluate the second one as a way to check your answer?
You certainly could, yeah. Yep, you could. Okay. Okay, segment bisector then. So a segment bisector could be anything. It could be a ray, it could be a line, it could be a plane, it could even be a point that intersects a segment at its midpoint. Okay? And creates, so there's an example right there. That's line, that's kind of messed up, but, oops. Well, I don't know, you can't really see. That's line K, isn't it? Right? That's actually something I might want to bring up here. How would we describe this segment down here? Segment AB. Good. Okay. How do we write that? Just a quick review from last week. How do we write that on a piece of paper? What would our symbol be for segment AB? Okay, good. It's going to be AV with a line, no arrows over the top, right? How would we input that into Moodle? And then capital A, capital B for the points. Good, okay? All right, what about this one right here? What's that line? Okay, good. You can't see it because it's hidden behind this other text, but there's a little cursive K there. And this is really typical in geometry. This is kind of the convention that we adopt in geometry. If we attach a symbol to the line itself, not necessarily to a point on the line, but just to the line itself, and typically we're going to make that a script lowercase letter, like K, then we can also write this in a different way. We could write this as line K in Moodle, or we could write it just as, let's see, we could write this as, boy, that's just like that. We want to also. That's a line. Okay, make sense? All right. Back to business, though. So these are all things that could bisect a segment. All right, find the midpoint of that. I want you to try this once. I'm not going to give you any formulas at all. I just want you to think about this. So we've got the midpoint of, I need to add something here. I need to add that symbol, don't I? The midpoint of segment SP, if S has coordinates -3, -5, and P has coordinates 5, 11. Just try that real quick. Try your hand. See what you can come up with on your notebook. Then we'll talk about a formula in a second. I want you to think about it a little bit first. Anybody get an answer?
Yeah.
Want to try? Avery, what'd you get?
I have like halfway between like the distance is like 8 square root 5.
Okay, do you have the coordinates of the midpoint? Okay, did anybody get the coordinates of the midpoint? Lily, what'd you get?
4, 3.
4, 3. Okay, how'd you get that?
The number between -5 and 11, and the number between -3 and 5.
Okay, so how'd you get 4 as the number between? You're on the right track. How'd you get 4 as the number between -3 and 5?
Because 3 from 0, and then yeah, I just got it.
Okay, so you added. So what you said was 3 plus. So you said this distance is 3 and that distance is 5
From 0.
from 0, and then you added them up and averaged them.
No.
Okay. So you got 3 and 5. Huh. Okay, I'm just curious how you got that. You're on the right track. Does anybody have a slightly different answer? What'd you get?
So delta x is 4.
Half of delta x is 4.
I think it was between these 8.
Oh, okay. Now I see where you
What is
did this.
delta? Yeah.
So it's half of delta x. I got you. So 4. What was the other one? 5. 3.
Well, actually, I think it's at 1.
Yeah, it's 1.
Well, okay, right. And it's, but that's the right way to look at it, though, isn't it? Because what we're trying to do is we're trying to find the average value, average x value, and the average y value, aren't we? If we think about what this looks like as a picture, if we go between 2 points, and we don't have to be that accurate, but -3, -5, if if I just throw that up on the XY plane, -3, -5, so I'm kind of over here-ish, aren't I? So right about there, kind of, right? There's -3, -5, and then over 5, and then up 11. Yikes, that's gonna be way up here. But I won't draw it to scale. So there's 5, 11. If I connect these with a segment, then we can all see that the midpoint's got to be somewhere kind of in there, doesn't it? Right? And it's not to scale, so don't try to count how far over and up that is. But if that's the middle point, wouldn't you agree that to get from -3, -5 to 5, 11, if the ant is walking along this segment to get there, when he's gone halfway, he's going to have changed his x value half of the total amount that it's going to change in the trip. Agreed? And he's going to have changed the y value half of the total amount that it's going to change in the trip, right? Well, how do we find the halfway point between two numbers? Isn't that what we just call an average? Right? So what's the middle value between the numbers 10 and 16? 13. How'd you get that? Okay, because you in that case you can see that it's just 3 away from both. Okay, how about this one though? What's going to be the middle value of the numbers -2 and 21? See, what's going to be? Not quite. How'd you get 9.5? There you go. That's how you average any two numbers, isn't it? When you average a number of numbers, you add up the numbers and divide by the number of numbers, right? So we could average 5 things by adding them all up and dividing by 5. Average 2 things by adding them up and dividing by 2, right? So if we want to get this middle value, then aren't we really just, do I need to say that again? Was that too fast? There's a lot of middles and averages there, wasn't it, right? So if I want to average two numbers, I just take their sum divided by 2, right? So if I want to average the x values to find the middle x value, what's the average of -3 and 5? 1, isn't it? Because it's the sum of -3 and 5, they add to 2, divided by 2 is 1, right? What's the average of -5 and 11? 3, because -5 plus 11 is 6, divided by 2 is 3, right? Make sense? So that's really all we're doing. A midpoint is just the average x and average y value. Now, what if we extrapolated this into 3 dimensions, right? Which the book doesn't do, but you guys can think about it. You're fine with this. What if we went from this point out to this point, like right here? Now, what are we going to add to that process? We've got to average the x values, the y values, and the z values. It'd be the same thing though, wouldn't it? Right? Does that make sense? It's really not much harder to even do in 3 dimensions than it is in 2 on a plane. Okay, good. So here's the formula. But you know how I hate formulas. Don't memorize a formula. Think about it in terms of what it represents, not the formula. You'll forget the formula, but you won't forget the concept. So if we're saying that the endpoints are x1, y1, or I should say x sub 1 and y sub 1, x sub 2 and y sub 2. And what do the subs mean again? The sub 1 and the sub 2s, what do those do for us? Yeah, it just keeps this index, just keeps track of what are we going to call point 1 and what are we going to call point 2. So they're different points. Then what is this really saying? This is the midpoint formula. Well, what does that mean? x1 plus x2 over 2. What's that really doing? Yeah, it's just the average x value, and then the average y value. That's really all that formula says. And if you think of it that way, you'll never forget it. Okay? All right. So this is one we just did, right? We added them up. -3 plus 5 is 2 over 2 is 1. -5 plus 11 is 6 over 2 is 3. So the point has coordinates 1, 3. Okay? All right, got a little trickier one for you. Try this. Now, this time it tells us that the midpoint of segment AB, the midpoint, has coordinates 2, 4. One endpoint is A, right? The other endpoint is B. One endpoint, A in this case, has coordinates -1, 7. Find the coordinates of B. Go. What do you think about this? When I say go, I don't mean necessarily start writing. I just mean I want you to stare at this and think a little bit before you write. Think about your strategy here. You get an idea? You can approach this? Emma, what do you think?
5-1.
5-1. How'd you get that?
Good job.
Yeah.
You double the coordinates of M, and then you look at A and see how far away it is.
Okay, so you said, let me kind of restate that. So you said that the x coordinate changes by how much to get from the endpoint A to the midpoint? The x coordinate changed by how much? From -1 to +2? 3. Okay, so how much does it have to change from the midpoint to the other endpoint then? 3. Good way to think about it, right? So 2 + 3 is 5. Good. So we know that the x coordinate of B has got to be 5. By the same token, how much did the y coordinate change? Okay, -3, not 3, -3, right? Because we go from +7 to +4, so it decreased by 3, right? So then it's got to do that again from the midpoint to the other point. So 4 plus -3 is, whoops, good. That make sense? That's a great way to conceptualize it, to think about it in a way where you kind of did the algebra internally. I like that. Mental math is huge. If you can get good at mental math, you get good at math. They go together. So let's look at maybe just a slightly different approach to getting that same answer. Let's look at a strictly algebraic approach. So algebraically, we could start with the midpoint formula, couldn't we? Just the average. We know that the average x value and the average y value give us the coordinates of M, right? What do we know and what don't we know here? What are the things we could plug in? Okay, we know one of the points, don't we? We know, say, x1, y1, right? So then couldn't we set this up so we know that the average x value has to be 2 and the average y value has to be 4, and we can substitute for x1 and y1 -1 and 7, right? And then look what that gives us. That gives us two separate equations. Well, it's going to start off with one equation. But when I point to this equation, how many variables are there? 1. What do we always say about an equation? If I can point to a single variable, I can isolate it. Good. So what are the steps in order to get that x by itself? Multiply by 2 to undo the division, and then add 1, and we got it, right? So there's, algebraically, we got the x coordinate is 5. Same thing here, right? Multiply by 2, so subtract 7, and we get 1. Okay, make sense? Okay? All right, we've got to hustle through this here. We don't have much time. But remember what I said also last week, kind of a bizarre statement about linear land and Angulvania, right? Anything we can do in linear land, which involves distances, right, and lengths, we can also do in Angulvania, which involves angles. The equations and all the concepts are going to be exactly parallel, no pun intended. I mean, they're going to get really just parallel constructions. The thinking we do in linear land is copied in Angulvania. So what do you suppose an angle bisector is? Well, yeah, instead of cutting a segment in two, it's going to be something, maybe a line, maybe a ray, maybe a segment, but it's going to cut an angle in two, right? So here we've got angle, how do I say that angle? ABC. Okay, and if we introduce a ray BD in this case, BD bisects that angle if the two smaller angles are congruent, which means that their measures are equal. Good. What are these little loopy things here? What do those symbols mean? Okay, they're angle congruence symbols. Okay, so angle congruence symbols, and they're not drawn very well there. They're supposed to look more like this. Okay, but one loop goes with one loop. An extension of Jill's question would be, what if we had another situation over here where we had two different angles that were congruent? Then we do use two loops. Okay, make sense? Okay, but we'd say that angle BD is an angle bisector of angle ABC. And we can do all the same stuff. So if we know that the measure of angle, the big angle, EFG, is 120 degrees, altogether here, what's going to be the measure of angle EFH? 60, right? It's got to be half. Agreed? And we could do the same kinds of tricks where I could throw in some algebra stuff, and it wouldn't be any harder. What's the equation going to be that's going to allow us to solve for the entire big angle?
4x plus 40 plus 20.
Good. Just set we know those are, this big angle's been bisected, so those are equal measures. Set them equal to each other. Solve for x. No big deal for you guys. Add 20, divide by 2. So if x is 30, then this angle is what? 70, and so the whole thing must be 140. It's not drawn to scale, is it? Is that a problem? No. We should never assume that anything in geometry is drawn to scale. Always assume that it is not. Okay, one last thing I want to just show you here. I had to make a little change. As I was creating some newer and better problems for the next section, I realized that the way that we were representing angles wasn't going to work. So starting on section 1.5, we're going to make a switcheroo. Instead of writing angle ABC, instead of writing it like this, angle ABC, we're not going to do that anymore in Moodle. Starting on this newest assignment, we're going to write things like this. Just like we did with rays and segments, we'll just write angle and then put the points inside the parentheses. And for reasons I don't really want to explain to you, it just has to do with programming. With these things. And then, okay, if you ask for the measure of an angle, that's a good question. We haven't gotten to that point yet. Let's see, that'll probably the thing that's going to make the most sense is just going to be to put an M out in front. Okay, good question, man. When we get there, Kirk, you won't have any of those in this assignment. When we get there, I'll let you know, though. Yeah. Yo.